we have Tucker McElroy, and he is presenting seasonality diagnostic based upon multi-step ahead forecasting errors.
Okay, here it is. Okay, so thanks for the intro. I'm going to keep to 20 minutes here. Okay, so I presented this basic material over a year ago in a JSM 2023. I've done some work since then, but so I thought I'd kind of move quickly through the main definitions of material, the motivation, heuristics, and the definition of the measures, and then get into the newer stuff, which are some of the illustrations. So I've got some numerical results, and the newer stuff is how to do inference. Okay, so, oops, my bad. Overview. So, well, everybody here probably is familiar with all of this, the presence of seasonality, and they were seeking to estimate and remove it. However, there's still ongoing research in how to measure, define seasonality, because at least there's several different diagnostics. Each measures different facets of seasonality. So this research was to propose yet another concept for how to measure seasonality. And I'll get into some of the features of this new measure. Well, there are many available diagnostics. Model-based F is popular that tests for seasonal means in a linear model of time series errors. So that's good for testing for fixed seasonality. The QS diagnostic that Maraval introduced is based on seasonal lag autocorrelation. There's also the old visual significance diagnostic with David Finley based on looking at spectral density. And I have some more recent work on autoregressive roots as a way of assessing presence of seasonality. So those are some that are available, not all necessarily in X13 ream seats, but at least there's code for doing these things. Okay, so in terms of criticizing these a bit, let's see if I can minimize that. Okay, so all the diagnostics first you have to postulate a form of the process in order to define the diagnostics. That could be a regression ream model, or at least having a different stationary time series process. The root diagnostic, you have to have an autoregressive form, so that's even more specific. And the diagnostics assess different types of seasonality, fixed versus dynamic. QS has a problem where it can classify non-seasonal processes as seasonal, so that's obviously a big strike against it. And then there's the communication issue. So it's frustrating. I've got like a lag in my advance to my screen here. Oh, good night. Okay, so the goal here is I want to define a new seasonality measure with the features that I can give some sort of intuitive conception of it that also specializes to familiar properties. When it specializes to familiar processes, it has the properties that we expect. And I'm going to look at seasonal persistence and intraseasonal association as the two key concepts, and the diagnostic should be scale-free as well. So using straight seasonal autocorrelation can have a problem. I mean, this is the sort of beginning idea. You want to have tight association between data that are S time units apart, where S is the seasonal period. And that could be assessed through seasonal autocorrelation. However, non-seasonal processes such as an AR1 can have a high seasonal autocorrelation. So that's a problem. That's problematic. So the idea I introduced here is intraseasonal association. Accounting for that intraseasonal association can modify this seasonal persistence idea and sort of screen out cases where seasonal correlation is coming through the season-to-season movements, such as happens in the AR1 case. Okay, so the basic idea here is seasonal persistence, I'm going to modify this lag S autocorrelation. Oh, actually, before I get there, first I'm going to define the seasonal persistence. I'm going to condition on the past, which isolates looking at the current observations. And if you do this, then you end up looking at covariance of forecast errors and S plus one step ahead with a one step ahead. So this will also really remove time dependence on the seasonality measure, since forecast errors typically are going to be stationary. So that's the first kind of idea, the seasonal persistence. And then we modify that by accounting for the intraseasonal association. It has some arguments in the paper about looking at S-step ahead forecast as sort of an assessment of intraseasonal association, and that's what we want to control for. So I'm moving through these slides a little bit fast, but the gist of it is we come to a measure omega. This is the seasonal persistence, and then I subtract off a second term here, which accounts for the intraseasonal association. Now it looks a bit messy, so it actually can be rewritten as this above formula, where I'm now introducing the conditioning upon not only the past, but the process at time t plus s. So this is the measure I'm proposing. It has seasonal persistence that accounts for intraseasonal association. And then this next slide is just that there's a scale freeform. So instead of looking at conditional covariances, I look at conditional correlations. And then this is going to be a measure taking values between -1 to 1, 0 indicating no seasonality, positive values indicating seasonality. Okay, so that's the general form, and then I can specialize to looking at different stationary processes, or first, as a first step, consider a process where the forecast errors are stationary. And then I just have a notation here for the covariance of forecast errors. And so then this seasonal measure takes this fairly more simple form. You're looking at these various partial covariances and comparing them. And the upsilon here is the normalized forms. So that form is a little bit more complicated, but it's given there for completeness. So important thing here is this doesn't depend on time anymore. I've isolated this in this special case. Furthermore, for like a different stationary process, so this is familiar to many people here, after we difference xt with a differencing polynomial, we have something stationary, and the MA infinity representation is commonly exists and could be written in terms of this psi power series acting on white noise. And when it's represented in that form, these covariance of forecast errors take a very simple form. These x's are just the coefficients when we expand the power series of the MAN form divided by the differencing operator. So those are the things that are easy to calculate for various kinds of ARIMA and SARIMA processes. And so then there's a slightly simplified form that the seasonal measure takes, given here. So I wanted to just show a couple examples for an AR1 process, which is non-seasonal. The seasonal persistence is phi raised to the power s. That's a problem because that's a non-zero value. When I correct the seasonal persistence for intraseasonal association, I get the omega measure, and the measure comes out 0. That's what we like. Okay, so now it's correctly saying there's no seasonality for that process. Let's get this. This is a cyclic AR2 process, which it does exhibit seasonality, and the omega measure is positive in that case. But a more easier case to grasp is the seasonal autoregression of order 1. That is seasonal. You suppose this parameter phi sub s, some positive number, and maybe pretty close to 1. Then in this case, the seasonal persistence is proportional to phi s, and there's no problem with interseasonal association. So the correction by that doesn't change the value. And so I just get phi s, and the normalized form is here. So that's good. That this measure is indeed giving you positive value for this seasonal process. And I'll go through this, and I'll skip down to the airline process. So here we have a seasonal difference followed by a regular differencing, and the moving average power series is given here, psi. And so we have the regular moving average and the seasonal moving average parameters, theta 1 and theta s, coming into play in this very kind of a complicated formula. It's a bit opaque. So what I did is I plotted the values of this seasonal measure as a function of theta 1 and theta s in the case of quarterly data. And so what we have here, vertical axis is the values of the omega measure. So higher values are more seasonal. And it's taking values, it's going up to about 2, and it's coming down to about 0 at the bottom here. And on the left is the seasonal theta. So as that's increasing, the seasonal measure is going down. So that should be somewhat intuitive, because that increasing of that seasonal theta, it's tending towards a cancellation of the seasonal differencing. And so it's the dynamic seasonality is being wiped out. Although you can still have a deterministic seasonal regressor being in play. And then the non-seasonal theta is on this other axis over to the right here. And so actually, as it increases to a positive value, it's actually increasing the seasonality a little bit, because it's tending to reduce the interseasonal association. But that's only up to a point, and then it starts coming back down again. So I found like, okay, this is sort of seemed like intuitive behavior to me in terms of how the airline process would behave, how its seasonality would behave as these two parameters are varied. This is just the upsilon form. So this is the normalized form, taking values between -1 and 1. So you can see that you can get pretty high values, 0.8's pretty close to the max. Okay. So next thing to talk about, so it's possible to analyze the Riemann processes in terms of the roots of the autoregressive polynomial when you think about the, say, an ARMA, autoegressive, there's a typo there, when you think about the ARMA form. And so there's a relationship between the measures I've introduced and these AR roots. So it turns out it's a little bit complicated to put into slides. There's a few formulas I left out here, but the seasonal persistency is driven by these autoregressive roots when they have near unit magnitude, and their frequency, their argument is close to a seasonal frequency. And then the interseasonal association also comes into play. There's a relationship there as well. We can relate the seasonality measure to visual significance, root, and the QS diagnostics. I have a few bullet points here. Basically, the QS has a problem I alluded to with seasonal autocorrelation. And then both the root and the VS, well, visual significance, basically you get a peak in the spectral density corresponding to autoregressive roots, magnitude close to the unit at the corresponding seasonal frequency, and that in turn is linked to the seasonality measure. So this seasonality measure is capturing behavior elicited by these diagnostics. So I'm arguing that in a sense it encompasses the VS and root results. Okay, so now for the kind of more new part. I won't say a lot about this. I don't have too much time left, but the inference, basically, I want to estimate omega s by using covariances of forecast errors, which would be, or sample covariance as such, and those would be computed in sample. And so there's a sort of complicated central limit theorem for these estimators. The asymptotic variance is a little bit hairy. And you have to estimate some quantities in the asymptotic variance. But I noticed that for testing, all you really want to do and want to just the sort of cross product thing. Okay, so the product of these two covariance or partial covariances equal to the product of these two guys. So I thought, okay, I proposed this estimator here. That will tend to zero probability under the null that there's no seasonality. And this also obeys a central limit theorem with unknown variance. So because the variance is unknown, I want to have a plug-in estimator for it. Or another way to do this is to just studentize. And studentization I use is based on some work by Jiafeng Shao using partial sums of the mean statistic. And this requires a little bit of care to do this. It wasn't because there's sort of like a product of two sample moment statistics involved here. So it requires a little bit of care to design this. But it does work. I get this asymptotic limit involving a quadratic function of Brownian motion after you prove a functional limit, central limit theorem. And so that's basically the basis for the test statistic. We would take theta hat over square root s. That would be a test statistic of mu z equaling 0, where mu z is just omega s in this case. Okay,
5
so
minutes,
that's
Tucker.
Yeah, fine.
Good.
Which I think will be done early. So that's in a nutshell how the asymptotic results work out. I simulated that null distribution and then used that just to do a quick sim of size and power. So I looked at simulating this SAR1 with this parameter of 0.8. And to kind of mimic the size, this is a little bit weird how I'm doing it. Really, I should be simulating a non-seasonal process to do size. But I just took that SAR1 and took the test statistic centered by 0.8 and to see kind of how it's performing. And then also set mu z equals 0 centered by 0, and that should give me power because it should be exploding up to positive number, positive infinity with at rate square root of sample size in that case. Okay, so in the first column, I have the nominal levels, and then what the test statistic is giving you, and this is for 20 years of quarterly data, so sample size 80. And see, I'm coming under these nominal levels, not by a huge amount. So I was not unhappy with that result. And then for the power is actually, I thought pretty good for sample size of 80. Granted, 0.8 is a substantial departure from 0 in terms of seasonality. So that's the very quick numerical study. But in summary, what if the research I'm presenting here, so the new things are the seasonality is defined through the seasonal persistence that is not explained by intraseasonal association. So accounting for that intraseasonal association is really important. Otherwise, you misclassify some non-seasonal processes as seasonal. And then I have these sort of notions defined here. C is the straight seasonal persistence. Omega is the measure that accounts for the intraseasonal association, and upsilon is just a normalized form. And so these are taking kind of the values I was hoping they would have on serine processes. That's because the 9 other things I tried that didn't work, I'm not showing you. I'm showing you the one thing that did kind of work out. So then in terms of future work, I want to look at a couple more types of processes, seasonally heteroscedastic and Regorima stochastic seasonal means processes, just to see sort of how the measures behave in that case. And then how does seasonal adjustment, once we seasonally adjust series, the seasonality should be gone ideally. So I want to see how the measures perform in that case. And then there's be a lot of empirical testing to do. So that's the presentation. Thank you.
Great. Thanks, Tucker. We have several minutes for questions, if anyone has any. Tucker, from the production side, I'll ask a non-super mathy question. Do you have any like tangible examples of, or an easy example that would apply to the lag, or is the general thought that there's probably a lag of this in many series?
The lag?
Like the intro seasonality.
Um, I mean, I guess kind of my next step is just take any like of our seasonal, any of our time duration production that are monthly or quarterly, and apply this, and then apply, compare it to the other diagnostics. But I have a couple more steps to do to make the implementation, like because I have kind of a code for just specialized cases, like the SAR one, but I need to have code for a general SARIMA model. And there's a couple of steps that are sort of hidden away in the background there. You have to have, if you're doing it for SARIMA models, you have to fit the model, then you have to get the forecasts in sample, get forecast errors, So there's a couple of steps there. I don't think that answered your question at all, though. So
no, that's okay.
Sorry.
That was helpful.
Okay.
Any other questions for Tucker?
I'll keep my eye on the chat too. So
yes, looks
well,
like
related to I think it was about your last slide. Could you apply this to series where you just took out seasonal means or fitted a model with fixed seasonal effects to take that out as a way of testing if there's anything left after that?
yeah, well, yeah, I hope so. Yeah, so cases where you seasonally adjust by just doing regression, GLS, I guess. Yeah, I hope I don't see a problem with doing it, applying it in such cases. I was hoping to also have a framework that could be really a lot broader than SARIMA. So like suppose people made forecasts based on judgment, like potentially you could apply the same idea. I have a judgment forecast and the actual value, and I do this in sample. You wouldn't have a good inference theory in such a case, but one could still compute the diagnostic.
okay. There are a couple questions in the chat. We have about another minute. Jess asked, are there any drawbacks you could think of for this diagnostic?
I'm still working on the, I would like to do more work on the case of fixed effects and seeing how it works in those cases. So there's, some more work to do in sort of bridging that case. The results for SARIMA, where the seasonality stochastic, those I'm really happy with because it sort of gives the measures, the values of like a high value versus low value in the cases that I expect. In the inference aspect, there's probably more like a little bit of work to do to put the code together. That could be a drawback, but I'll put it all on GitHub and people can just use it.
Great. All right, I'll have you answer the last one in the chat so we can.
Sure.
Thanks, Tucker.
Yep.
Okay, next we have